All right, let's start with the meeting. Hopefully my screen is visible. So, good evening. Welcome everyone. Today we will delve into the fascinating world of planetary imaging. This specialized field in astrophotography allows us to capture detailed images of planets within our solar system, offering stunning visuals and valuable scientific insights. So, what we'll gain from this session? First of all, what is planetary imaging? Methods of planetary imaging, how we can collect our data, processing actual data, and future prospects and scopes in processing. So planetary imaging involves capturing high resolution images of planets, moons, and other celestial bodies. My screen is visible, right? Just want to confirm. Can anyone unmute and just tell?
Yep, it is visible.
Sure, nice, yeah. So unlike deep sky astrophotography, which focuses on distant galaxies and nebulae, planetary imaging targets objects relatively close to the Earth. This approach requires precise techniques and specialized equipment to overcome challenges like atmospheric turbulence and dynamic changes like planets' rapid rotation. Deep sky imaging requires comparatively sophisticated equipments and processing techniques, as galaxies and nebulae, though big in size, they are a bit faint. Deep sky imaging can be thought of as seeing a light bulb from several kilometers away, and planetary imaging can be thought as seeing a street light from a few blocks away. So what are the challenges in planetary imaging? Since planets are small in angular size, we need bigger telescopes to shoot them. Using telescopes with longer focal length gives higher magnification, showing a clearer view of the planet. In Kritika, we use our 8-inch Dobsonian telescope to shoot planets. It has a focal length of 1200 millimeters, and the upcoming Kritika Observatory, which will consist of an 11-inch SCT, a Schmidt-Cassegrain telescope, which is a combination of mirrors and lenses. It will have a focal length of more than double, that is 2800 mm. We'll be able to get clear views of planets like never before. But it's not as clear as we think. This is because with more magnification, the atmospheric effects are also more evident in our images. Atmospheric turbulence, or seeing as we say, distorts the images, making it difficult to capture smaller details. So how do we solve this problem? We can use adaptive optics. It employs deformable mirrors that sync with respect to the atmosphere in real time based on feedback from a reference star or laser. But we can't afford this definitely because it's too expensive. What we can afford is lucky imaging. It's got nothing to do with the luck and gambling. Lucky imaging is a form of speckle imaging technique in astrophotography that captures numerous short exposure images of a target. Here's a nice read by Carradine Observatory on lucky imaging. In fact, lucky imaging also excuses us from any tracking inaccuracies. By that, I mean we don't need to track accurately as the planet moves throughout the night sky. Using short exposure time minimizes the atmospheric effects, similar to how we use short exposures to avoid motion blur. We aim to capture as many short exposures in very less time. So how do we do this? We can do this by using a high frame rate video capture. In Kritika inventory, we have a Planetary camera ASI 224 MC Pro capable of taking high quality videos at 150 frames per second. Using softwares like Fire Capture or SharpCap, we are able to capture thousands of frames in the form of a video. Now we want these frames to be of the highest quality. Such high quality videos are saved in a format known as SIR. This can be understood as an analog of RAW for videos, which is mainly used in astronomy. You might know JPEG has got lossy type compression. A lot of the detail is lost as a compromise to save storage. MP4 also does lossy compression. Thus, we do not prefer this format. We use SIR instead, but it can take a lot of data. So you might need to clear your storage. All right, enough theory, let's get to processing. Before that, I would like to tell you that the data we are going to process is from Wido's Astro Forum, an online site where he has made his data public. Just a second. Yeah. Here is his website, and under planetary imaging, processing and Autostakkert. You can go down a bit. And here he has made his video of Jupiter publicly available. All right. So I will just log in with my other device for processing. My screen is visible, right? Yes, it is. Sure. So the process softwares that we are going to use to process are mainly Pipp, Pipp, Autostakkert, Registax and Gimp. This might look a lot for you guys because you are just now beginners. We can indeed do all these processes in only one software, that is Registax. But the reason for these two initial softwares, I'll explain as we go. Here's the video that I have installed from the forum. First, we'll open Pipp. We'll click on File, add a source file, go down and select the video and click on Open. Yeah, the first prompt that we get is, do we want to use a Bayer pattern RGB? So what does a Bayer matrix actually mean? So as you might know, color cameras have got a filter in front of them. This is a color filter which consists of a 2x2 array of RGB filters. So out of which one is red, two are green and one is blue. Why we use two green filters is because it is used to accurately represent how our eyes see. So green is just to increase the luminance. I can show you a pic of Bayer matrix as well. So this is how the Bayer matrix looks like. Now it is important for us to de-Bayer the image so that we can properly convert the raw data from the camera sensor to color data. This is done by choosing the correct Bayer pattern. In this case, we know because the camera has RGB pattern, so we'll click on yes. But in most cases, we want to actually input it according to ourselves, so we click no. It is important to de-Bayer the images because if we don't do that, then while processing and sharpening, we can get grid-like patterns on our images, which don't look as appealing. So we'll click on yes for now. And as we can see, the image is loaded here. So you might notice the initial video, which was given by the person, was looking kind of desaturated, black and white. This is because this is in raw format. What Pipp does is it enhances the color slightly by increasing the saturation, and it has also done debayering. which gives the image a much more colored or saturated look. Still, this image isn't as sharp as we intend it to be, so we'll have to process it further. So in Pipp, we'll firstly click on batch mode. In optimize options for Planetary, in our case, because we are editing Jupiter. In case of International Space Station, which people do shoot from ground, we'll click on ISS. For a solar lunar close-up, like craters of moon from nearby, we can click on this. Or if it's a full moon or a wide image of moon, we can click here. So here's Planetary. Later, we'll go to output options, and in output format, we'll select the file format which the input video was of. So in our case, it wasn't actually SIR, it was AVI. AVI is also a popular multimedia format similar to MP4. So the output format should be the same as it is input. So we'll click on AVI. Then we'll click on processing options. We'll click on object detection enabled. This is so that the Pipp software's algorithm can properly detect the objects. Object detection threshold can be set to automatic and center the object in each frame. So the purpose of Pipp is actually so that the Jupiter in each subsequent frames is centered nearly in the center, right? So as you might see, due to some tracking inaccuracies, Jupiter might move from left to right in all the frames. What Pipp does is it centers the Jupiter in all the frames so that our further processing can be a bit more with ease. Here center the object in each frame, you click on none. If we want it to be centered a bit to the top left or somewhere else, we can click here. So enable cropping, for now we'll disable it. What enable cropping does is it makes a box tightly fit around the planet and it crops the video. We don't want it, we want the black space also around it. This feature is useful in case we want to process heavy videos. So we can just crop the image and that will reduce the computational time. Finally, we can go to do processing and start processing. So what I've done is already run the process previously. We are processing 3,379 frames in this video. This might take a bit while, but we can skip this step actually because I've already processed this image right over here, the video. Yeah, so this is the video by Pipp, and you can see all the frames are like properly centered in the video. So we are like done with the first part of processing out of the 4 softwares that we are going to use, and you can just get over with this and start with Autostakkert. So Autostakkert is the process where the actual lucky imaging comes in way. So we'll have to first select the directory where our video is. Here's the Pipp output. It's already open over here. Right. So this is the output, and here we can see Jupiter. And what this window represents, it's just for representation purposes and to set alignment points. We'll come to that later. And this window actually gives a really nice interface showing all the steps. So first we have opened the file. Now we have to select on image stabilization. What this means is we have already centered the Jupiter in our frame in Pipp. but we further want to stabilize the video. So in case of lunar details, we can click on surface for close-up of craters or something. Uh, Click on improve tracking. So if the video is like wobbling around, we can stabilize it even further by improve tracking. Click on expand. But for in our case, it's moon, it's planet center of gravity. So center of gravity actually is just for names purpose. It's so that the software actually uses a similar kind of algorithm similar to calculation of center of mass. So what it does is it takes the pixel values on the same axis, for example, x-axis. It calculates the center of mass, so which will be roughly in the center here, and it does this for like y and x-axis respectively. So we can get the center of that planet respectively. Now these pixel values aren't actually ranging from 0 to 255 as we might know, but they are ranging between 0 and 1. So it's either black or white. Otherwise, some brighter parts of the planet might have more weight to them. So the center of mass might shift a bit over here. So it's working is a bit more complicated than this, but for simpling stuff down, this is how a COG algorithm works. And we'll click on dynamic background. Secondly, we'll go to quality estimator, in which we'll click on automatic. If we want to have a bit more manual control, we can click on local and AP. Your AP means alignment points. We'll get to that in just like a few minutes. Second, we'll click on analyze. So this process might take a bit while. Meanwhile, you guys can ask any doubts if you have, because it's a bunch of detail actually. Just yeah. So you can just unmute or type in chat if you have any doubts. Okay, I suppose there are no doubts, and we are done with processing as well. So let's get to the next step then. So here we are going to select a reference image for processing. So in the entire video, there are total 3,300 frames roughly, and we want to select one really good image so that that can be used as a reference for stacking other frames, right? So in our case, we are going to use the automatic feature, as the software does a really nice job in pretty decent videos like this. And manual if we want to have a bit more freedom in case the video becomes a bit blurry in between, and we don't want to risk the software choosing that frame itself, right? But in this case, we can see the video is like pretty decent. All the frames are relatively neutral. So we'll click on automatic. Now the graph that we get as an output over here represents the quality of all the images. You can see there are two graphs over here. One is the gray one and one is the green one. So the gray graph represents the quality of images before sorting. So this represents actually in the ascending order how the frames are. So this is the first frame, this is the second, and so on till like 3,379. And the green graph is the sorted frames. So this is the frame of highest quality and so on, and this is of the lowest quality. Now we don't want our frames, like in general, we use stacking so that our image at the end is really sharp. So ideally we would want all our frames to be stacked so that the average of all the pixels can be taken and the final image is a bit more sharp. But we can see some frames are a bit better and some frames are really bad. So we don't want to stack these frames. So we want to stack a particular percentage or a number of frames. That we can do from here. Frame percentage to stack and number of frames to stack. Now we can get multiple outputs. In fact, 8 in total. Here we can select, for example, 60 and 40. That is, first output will be of 60% and second will be of 40%. Here's the output for the output image, which will be the stacked image. It can be TIFF or a FIT. or a PNG. PNG, as you might know, is a popular format, but TIFF or FIT can be less heard of. FIT is a high resolution image format, 16 or 32-bit. It's popular in astronomy mainly, but we are going to use TIFF as it is widely used in like softwares like Photoshop or GIMP. Normalize to stack is a good feature to do, but in this case, we won't delve into this. Sharpened images is something which we want to manually do in Registax instead of here. So this will like automatically sharpen our images using the algorithm in Autostakkert, but we want to manually do this. There's also a feature to blend this with the original image. So like if we feel the sharpened image is like a bit too crisp, not natural looking, then we can blend it with the original image as well. RGB align is a good feature to have in case some layers of the image like green or something are slightly offset from red and blue. This might give edges of the planet a look bit too green, like this edge is a bit green, this is a blend of red and blue. So for that we do RGB align, but in this case the individual frames also look pretty decent, so there's no need for this. Then we can enter a field output feature. So this is the naming of the image. We can add anything over here at the start, but the default is also really nice. So this is actually super resolution or drizzling. It's an advanced technique in astrophotography, which has to be done subsequently with dithering. In our case, planets are automatically doing that, but we won't dwell into the workings of this as this course doesn't cover that part. Now we can go on to selecting alignment points. So alignment points are actually so that it helps the software to recognize some of the features on the planet's surface and distinguish them from the subsequent frames. So it will try to align some of these bands on Jupiter, or if the great red spot was visible over here somewhere, it will help it to identify that part in this image and how much shifted is it in the next image. So these alignment points are used to like distinguish these small features. This might look like a huge blur to us. So aligning 3,379 images by ourselves is a huge task. That's why we use the software. So setting these AP grids, we can use different sizes. Usually I go with smaller sizes because in our case, the features are a bit small. So 48 seems to be a good number. And this represents a scale for the brightness threshold. So if I go down like 0 and select place AP grid, you can see the entire screen is filled with this grid. We don't want this. This is because this threshold is set to 0. So this will include all the pixels in the image. If I set it to like 100 or something higher, the AP grid is a bit focused to the center where the most bright pixel value is. We don't want this as well. A good number can be like 20 or 30. In this case, it is covering the periphery of the planet, and we don't want this as well. So we can increase a bit more. Yes, this seems like a good number. And this is good. So you might be curious, what does this graph represents? This is also a quality graph of the planet, similar to this one. Now we can click on stack. Again, this process might take a bit while, so you guys can ask if you have any doubts meanwhile. If not, then I can show you a bit more resources. Okay then. Yeah. So there's a nice channel, www.geb. He's got really nice image processing videos on Planetary. These softwares that we are using actually are pretty old. So Okay, it's automatically turned off. I'll have to log in again from my other account. Just a second.
Meanwhile, if you have any doubts, you can write them in the chat.
Yeah, sure. In fact, I can share screen from this one. My screen is visible, right? And even
Yes.
okay, nice. Just a second. So this is a really nice channel. As I was saying, these softwares are like pretty old. Like some of them are made in 2011 or something, but they are still relevant now because we still use them in field. These videos are also pretty old, about 8 years old, but this guy has explained these softwares in like really good depth, and the videos aren't also too long. Like some of them are less than half an hour or 15 minutes, so you can have a really nice go at it. I've tried to cover all these softwares in a really short while, but this person has explained them in like super depth. So if you want to get to know about these softwares a bit more, then have a look at this channel. And other than that, I would like to show you other processing softwares as well. I know four have been a lot till now, but one of which is pretty nice to use is WinJupos. So as you might have noticed, even after stacking, the images might not look as sharp. This is because we haven't included features like rotation of the planet. As you might know, Jupiter rotates, has a rotation time period of 10 hours in Earth's time. So it rotates pretty fast. And a video about a few minutes long, having a few thousand frames, can have some frames in the start being at a different position from them at the end. This is because the planet rotates pretty fast. What WinJupos, a software, does is it derotates the frame. The algorithm doesn't work as simply as this, but it makes sections about the longitude of the planet, maps them, and stacks them accordingly. So this makes the final image a bit more sharper as well. A pretty interesting project done by this astrophotographer, which got the astronomy picture of the day 2 shout out as well, is making a map of Jupiter. He has done this by using WinJupos and mapping the planet as it completely rotates about its rotation time period, 10 hours, and made a map of it. He has also made a polar projection of the planet, which can be easily done in WinJupos as well. This is something pretty interesting. Right. I just try to log in with my other PC meanwhile. So the process isn't over yet, but I'll try to show you some other resources online. You can actually process NASA images. These images are open source and can be easily accessed from net. So if you just search planetary images NASA data, and just a second. Yeah, so this is a nice link. I'll share this in a folder actually later on in a Google Doc, all these resources. So this is a nice article by BBC Sky at Night where they have described how you can access this data. And as you go down at the end, these are the resources for from where you can get the raw space mission data. So the first one is the Lunar Reconnaissance Orbiter mission data. From Mars, the Curiosity or the Opportunity mission data. Saturn, the Cassini mission. So for example, I'll just open this and show you guys. So the data over here isn't actually colored. It's in black and white. More about it you will learn in the next processing videos actually. So you can select which date to which date you want to filter out the data. You can select Saturn or any moon of Saturn that you want, and there are other filters which you can select, color filters, narrow angle, wide angle, or anything, and the data is free of cost to download. The processing workflow that we have covered as of now isn't as in depth to process black and white images. We'll learn more about it next week. Next week's processing video will be more towards processing deep sky images. So it won't cover processing planetary images from NASA space missions, but you can employ similar techniques to uh, process these as well. Right. So if you guys might have any doubts, you can ask. Tab tak. The process is almost about to be finished, and we are done like nearly more than 50% of the processing. The final steps are Registax sharpening and final touch-ups in Gimp. So Gimp is just like a free version of Photoshop. You can say it's open and you can download the software. Photoshop is obviously paid, so most people might not want to get it. All the softwares that we are using over here, like Pipp, Autostakkert, Registax, Gimp. In fact, the ones in next week as well, like Cyril, all these softwares are free and you can download them easily. Yes. Just a second. The process is nearly done and hopefully you guys can see my screen. Yeah. So Autostakkert has saved its image in the same directory as we want. Here. Here are two folders because we selected here 60% and 40% of the top frames to be stacked. Those are saved in these two folders. We can have a comparison look over here between these two. So the image might not look as appealing as well now because this is just a stacked result. So it's like a washed out blur. We are going to do further sharpening and image corrections to it in Registax as well. What we now want to do is select the best out of these two. It might be a bit difficult to judge which image is a bit better. But according to me, the left one is a bit better. This might not be as obvious to you because it's on screen shared, so the resolution might not be as up to the mark, but we can select this one. So we are done with the Autostakkert. We can open Registax. So Registax is a pretty old software. It was made in 2011. All the processes of Pipp and Autostakkert we can do in Registax, in fact, align, stack. But these processes are pretty simple and the algorithms are pretty outdated. So we tend to use Autostakkert and Pipp for these steps. We can open this from select, desktop, Pipp, okay, not this one. Where's the other folder? Not this one. 60, Pipp, open. Stretch intensity levels, yes. The image is a bit zoomed in. You can click on show image to show the full image, and this is show processing area. So this box actually represents the amount of area that we are processing. This is just so that while trial and error and while sharpening the image, the computational speed is a bit less because we don't want to wait like 2-3 seconds just for the process to be done while tweaking these parameters. So like we can select the area in which we want to process. We want it to be the planet, so a bit in the center. All these features over here like histogram, gamma, color mixing, RGB balance, these all we will do in Photoshop or GIMP later on. Again, this software is a bit outdated, so these features aren't relevant to us at the moment. This software, however, is very well suited even now for wavelet regularization. So what wavelets does is it measures the frequency of the colors and the features in the image and sharpens them specifically. So I can show you over here. We'll select Gaussian instead of default and linear over here. And if we click over here, this can show us the features that are selected in each wavelet. So what does each wavelet mean? It ranges from a scale of 1 to 6, 1 representing smaller features, like really small features like grains, small storms or something, and 6 represents the larger features like the big bands or anything. Wavelets is not just something used in astro image processing, it is something widely used in image processing in general. So if I left click on this preview, you can see these are much more smaller features. If I click on 2, you can see the small bands or small storms. If I click on 3, the bands are even more evident. If I click on 4, they are even more evident. 5 and 6. 6 are the large scale features. So step increment represents how much difference you want to be between these features. So if I click on 0, that is 0 step increment, you can see this is 1, this is 2, this is 4, and this is 6. There's not much difference between them. So we want the step increment to be at least 1. If we set it like 4 or something, 3 or 4, then just a second. The difference is like a bit too much. Like by 4 itself, the entire planet is covered. By 5, it's just covering everything. The green section represents the part which is getting covered, and red is the part which we don't want to affect. It's like a mask. So we are just applying it so that we are limiting our process to only that region. So 3 isn't an ideal value, obviously, because uh, it's covering the entire planet. It's not localizing any features for us to process. So I think 1 was the perfect one. And here we can go ahead with sharpening. So if I exaggerate this, you can see a bit more sharpening is seen. In 6, it might be a bit more evident. So this is like the worst possible way to do processing. Like you shouldn't exaggerate any values. It should be really subtle. So tweaking it from 1 to like 2.4 is also a bit too much. What you can do is hover the mouse cursor over it, and using the arrow keys you can uh, fine tune these values. So 2 seems to be 1.9 seems really nice. You have to click it once. You can see the shadow behind the planet is a bit more distinguished. We don't want this actually. It gives it an artificial look, so we want to be really subtle with this. Usually a good way to process wavelets is having the smaller features a bit more sharpened than the larger features. So we can have one going to like 20, maybe two going to like 7. This is all subjective actually. This you guys can learn more by practicing or processing even more images. And you can check these boxes if you want to see before and after. So this is before, this is after. It's kind of a bit more artificial, so I'll just tone this down a bit more. Even less, even less. This seems good. Yes, this is a mild look to it, and we can click on do all. By do all, it actually processes the entire region instead of just this box. So it's done, and we can click on save image and name it Jupiter Regi for Registax. I didn't see the format in which it was saved. Okay. The format was if as we wanted. We can click on GIMP. This is the last step of our processing, and after this we are nearly done with it. So opening GIMP. Yes, so we can click on file, open, desktop, not this one, 60, Jupiter Regi, open. This is the Registax processed image, and in this case we are going to do our final adjustments like contrast, brightness, color balance. We'll go to color, and firstly we are going to do curves adjustments. I would like to explain the theory behind curves adjustments and histogram before we go ahead. So the graph which you might see over here is actually the histogram. Histogram is a collection of pixels, their brightness values to be specific, in an order arranged in an ascending way. So this is 0 and this is 255. As you can see in this image, there aren't any super white or bright pixels. So there's no graph over here as such. So even if we make any changes in this region of the image won't change a bit. The graph has got a value in the darker regions. It's just that it's a bit too faint, so it's not visible. And mainly the graph is concentrated in this region, that is the midtones. Curves can be used to adjust nearly everything in the image. It can be used to adjust the contrast, the brightness, the color, shadows, highlights, anything. So this is like the proper manual method to do it. We can adjust all these features using these individual processes as well, like shadows, highlights, brightness, contrast. But I like to start it out with curves. So if we like exaggerate the features like this, it just becomes white because we are brightening the histogram by stretching it a bit up. If I take this down, the entire image turns black. So I'm toning down the histogram. We don't want to do this. What is a good practice is to set points over here so that the curve behaves as we want it. 1, 2, 3. And then we can individually adjust these points like this. So if I do this a bit too much, the center becomes a bit bright and we don't want this. We want the image to be popped out, but not artificially. So this might seem good. You can see if I adjust in this white region, that is the highlights part. If I take this up or down, the image doesn't change as much. That's because there aren't any highlights in the image. If I take this a bit down, you can see the background becomes a bit more darker. This instantly pops the image out. So this can be a good curve. This is a popular curve known as S curve because of its shape. It is used mainly to increase the contrast in the image. I do this instantly, gives it a 3D look. We don't want the shadows to be really less because then it just crops out the edge of the planet and looks as if we have photoshopped it and just stuck the planet over there. We don't want it. We want it to be natural. So we let this settle. Yes. This looks like a nice S curve. We can take as much time as we want over here, but I'll just stop over here. Okay. Then we can go on with color balance. So in our case, the image looks like pretty natural and the colors are decent. But if sometimes the image might look a bit green, this can be because we are shooting from Mumbai and this data was taken from the Astro Forum, but Wido's Astro Forum. But in Insti, we are shooting from a bit more light pollution. So because of that, the image may tend to look a bit green or yellow. Green because the Bayer matrix has got two pixel arrays for green color, right? So camera is more sensitive to green color. So that's why uh, toning this down a bit towards magenta can be our choice. But in this case, I won't tweak the parameters because the image is pretty neutral at the moment. Here's the option to selectively uh, edit the color balance of midtones. That is the region in which Jupiter is. There are no highlights as such. So even by doing this, okay, there are a few highlights in the center. Then. Even by doing this, there won't be any drastic change. You can change the shadows color, that is the background, like this. This isn't at all natural, so we'll let this be at 0. Okay. Yellow can be a bit more, I guess. We can also change the color temperature, make it a bit more warmer, or make it a bit more blue. Blue doesn't seem right for Jupiter. A bit warm is better. Okay. I need shadows and highlights. Decrease the shadow a bit. brightness and contrast. We have done this in curves, but we can adjust it a bit more. Not so much, just one. Actually, no. I guess this is it mainly. This was a really beginner level tutorial of planetary imaging, and we can finally go ahead and save it. Saving this actually saves the GIMP instance, so we want to export it. We can select the file format in which we want to export it, and choose JPEG, name it Jupyter GIMP final. We want it to be of the highest quality and export. Saved in this folder. So I'll just show you a comparison from where to where did we process it. Okay. So one small thing that I forgot to cover is the edges might look a bit purple, right? So we can do a quick cropping also here, like this, for the edges, and export it. Final 2. Export. Open final 2. Then delete this one. Why is this purple again? Okay, we can do this later on as well. So you can see this was the initial image that we got from the Astro forum, and yeah, and this is the final image. The entire process might seem a bit complicated because we use 4 different softwares to process it, but it doesn't end over here. As I said, we can use much more better softwares like WinJupos to derotate the planet and get an even sharper image. Some of the images that you might see on NASA page like Hubble or JWST, those images might look like unrealistically sharpened, like they can look crazy sharpened. Like I'll just show you HST Jupiter, Hubble telescope Jupiter. Yeah. So this image might look really sharp. Why is this? This is simply because Hubble Space Telescope is a space telescope. It's outside of Earth's atmosphere. Not technically outside, but the atmosphere at that altitude is really less. So the distortion that we get over here is not as much in Hubble Space Telescope. In fact, it's negligible. So the images are obviously way more crisper. And one small question which I might ask you guys is, in all these images, why don't we see stars in the background? And any of you guys might be curious to answer it in chat or by unmuting. Any of these Jupiter or planet images, moon images, you don't see stars in the background as much.
Is it due to the exposure time?
Yes, precisely. That's because of the exposure time. As stars are actually pretty faint in comparison to planets, and even for shooting planets, as I said, we tend to use really short exposures. That's to avoid atmospheric distortion and blurriness. So we choose really high frame rate and short exposure videos. So that's why stars aren't visible actually. So if I like really increase the exposure, even in like post processing or something, by brightening up the image a bit too much, we can see like really bright stars in the background. Even they might appear a bit faint because planets are like really bright. Yeah. Okay, all right. I guess this was it. And if you guys have any doubts, you can ask them. In the process, any part might have seemed a bit vague or confusing. Any small doubts are also welcome. Okay, then if there are no doubts, I guess we can end the session. I'll make a doc in which all the resources, like from where you can download the NASA raw data, space mission data. I'll link all the resources in a Google Doc, and all the really good YouTube channels you can see and everything, and share it. Also, I'll give the link from where you can install the softwares. Like Pipp has actually taken down their page of installing. So there's a Google Drive from which you can install the installer. Okay, then we can end the session. Thanks a lot.
Thank you everyone for joining. If you have any more doubts, you can always DM us. We have just gone through 4 softwares in like 1 hour. Don't be scared by this. We also it took a lot of time for us to understand this as well. So if you have any doubt, feel free to contact us and DM us on WhatsApp as well.